Everybody, with Miss Smith. So today we're going to talk about phases of matter. I know you know about solid, liquids, and gases, but I want to go a little bit more into detail. Just kind of what makes up solid, liquids, and gases, how to go between solid, liquids, and gases. We're not really going to talk about plasma. There's not really a reason to talk about plasma at this point. But anyway. Then we're going to talk about just the basics of the periodic table. I'm just going to mention just a few things, and then we're also going to talk about mixtures, compounds, and elements, and how to tell the difference between those. So we're going to start off with opening our notebook. And so the last notes that we put in our notebook were about physical and chemical changes. So this is going to go on the next page right after that. So this is going to be called phases of matter. Okay, so we're actually going to make a chart. We're going to do 3 columns, solid. You know what? Let me give myself a little bit more room. Solid, liquid, and gas. So we've got 3 columns here. Actually, we have 4. We should have 4 because we're going to put some labels in this far left column. All right, so I want to give you the different characteristics of solids, liquids, and gases. When we have our exam in a few weeks, 2 weeks I think actually, you'll have questions like this that involve this chart right here. So this chart is actually very, very important that you get it in your notes and that you study this chart, because there will be many questions on your exam about this. Now, so the first one I want to talk about is the shape of a solid. Okay, so the shape of a solid is definite. What that means is, if you're talking about like a notebook sitting on a table, that notebook isn't all of a sudden just going to melt or just jiggle or something like that. What I mean is it's the shape of that solid is going to stay definite. Okay, it's not going to switch back and forth. I mean, yes, if you melt it, that's one thing. But if it's just sitting there and nothing's happening to it, there's no changes going on, then it will stay, keep its shape. It's a definite shape. Now let's look at the same category, but for liquid and gas. A liquid has an indefinite shape. If you were to have a water bottle, the water in that bottle takes the shape of its container. And then the other one, if we're going to talk about gas also has an indefinite shape. That also takes the shape of its container. All right, the next one is volume. So this is how much is there. So the volume of a solid is definite. So for example, again, we're talking about the binder sitting on a table. All of a sudden, that binder just doesn't get huge or ginormous. It's going to stay the same size. Now, for a liquid, the volume of a liquid is definite, but the volume of the gas is indefinite. Now, how you would see test questions about these two things would be, which state of matter or phase of matter has an indefinite shape but a definite volume? That would be a liquid. That's how you would see those kind of questions. All right, let's move on. Let's talk about particle distance. I'm just going to say particles. But if we're talking about a solid, the particles in a solid are wrong words here. Should say tightly packed. All right, those molecules or those particles are so close together. That's what gives it its rigid shape or its definite shape, is because those particles and molecules are so close together. Now, if you start talking about a liquid, they're a little bit farther apart. So we're going to say loosely packed particles. And then when we get to gas, they are very far apart. okay? So in a gas, you've got a lot of distance between your particles. That's the reason why the shape of a gas is indefinite, is because there's so much room between the particles, they can kind of move and do whatever they want. But in a solid, because those particles are so tightly packed, that's the reason why it has a definite shape, is because they're so close together, they don't have room to move. All right, next category is, will it compress? So I'm just going to call this compress. So what I mean by compress, if you think about, at the junkyard when they start compressing cars, it just makes it small. Now, a car is a solid, but when you compress a car, you're compressing all the empty space in that car. You're not actually compressing a solid. So I want you to think about this not in the sense of an object, but in the sense of the particles. Remember that the particles in a solid are really, really close together. When you compress something, you're closing that gap between those particles. So when it's a solid and you're compressing a solid, there's no room for the particles to come together. So you cannot compress a solid. So we're going to say no. Now, on a liquid, they are a little bit further apart. They're loosely packed, but it's really, really difficult to compress a liquid. The term is actually virtually incompressible. There are a few circumstances that you could compress a liquid, but it's not very likely. So we're just going to say, for all intents and purposes, that no, you cannot compress a liquid. Now, let's talk about a gas. Remember that we said no to a solid, that it can't be compressed because the particles are so close together. But a gas, the particles are very far apart, so that actually means they have room for the particles to come together. So a gas, yes, you can compress a gas. Now, the last thing that I want to put on this page before we go on is going to be a drawing. I want to draw the particles. So I'm going to draw a container for each of these. Drawing skills are terrible. Okay, so the particles of a solid are going to be really close together like this. The particles of a liquid, remember that a liquid takes the shape of its container but doesn't fill it completely. But a gas, however, takes the shape of its container, but it does fill the container completely. All right, a couple other things that I want to talk about solid, liquids, and gases is what happens when you go in between phases. What are those words called? Okay, so if you are going from a solid to a liquid, that is called melting. I'm hoping most of you know that one. Okay, let's try another one. Liquid to solid. That's called freezing. All right, nothing new. You know those. All right, what happens if you go from a liquid to a gas, though? That's called evaporation. And then let's go the other way, gas to liquid. It's called condensation. And then here's two that you might not know. If you go from a solid to a gas, skipping the liquid phase, that's called sublimation. That one is kind of rare. It doesn't really happen that often. In a lot of different compounds, but dry ice is probably the one you know the most. Ice is solid and it comes off as a gas. It completely skips the liquid phase. Now, what about the opposite of that when you go from a gas to a solid? That is called deposition. Now, something else I would like to talk about are types of solids. Okay, I'm going to draw a little picture here. I'm going to draw a picture here. There are two types. You have a crystalline solid and you have an amorphous solid. Now, the difference between these two solids, yes, the particles are real close together, that's what makes them a solid in the first place, but there's two types of solids. So the difference between those two, a crystalline is going to have a repeating pattern. Crystallines are very hard because their pattern is repeating. So we're going to like this. Repeats the same pattern over. Oh, I messed up. Over and over. Same pattern over and over. So that's a crystalline solid. Crystalline solids would be something like salt or sugar or rock candy or rock salt or anything that's a crystal. Really, diamonds are technically a crystalline solid. Now, an amorphous solid, their pattern is not the same. It's kind of just all over the place. It's not a repeating pattern. It kind of does whatever it feels like. All right, so an example of a crystalline solid would be a diamond. Okay, they're very hard. An example of an amorphous solid would be Jell-O. Okay, it moves, it's movement now. Jell-O is technically considered a solid. It's just an amorphous solid. It's got some movement, it's not very hard. All right, now the next thing that I would like to talk about is I'm going to draw another little picture. We're going to go a little further down, and then I'm going to PowerPoint that I want to go through just real quick. So let's organize matter for just a minute. I know I've given you quite a few terms, but let's organize it a little bit so we can get this straight in our head. So matter is characterized into 3 different phases: solids, liquids, and gases. All right, now from there, you have 2 options from there. You have what's known as mixtures, and you also have what's known as pure substances. All right, now it goes even further. There are 2 types of mixtures and 2 types of pure substances. Now, the 2 types of mixtures, there is a homogeneous mixture and a heterogeneous mixture. Now, how you know the difference between a homogeneous mixture and a heterogeneous mixture, you have to look at the prefix there, okay? Scientific words most of the time have prefixes, and if you'll break it down, you'll actually kind of figure out what it means. So homo actually means same. That's why homosexual is a term, and it means same-sex attraction. So that literally is a scientific term. Now, if you're talking about heterosexual, that means different. Hetero means different. So those are scientific terms. So we're going to say that a homogeneous mixture has the same composition throughout. Okay. Now, that means that hetero is going to have a different composition throughout. Okay, let me give you some examples of what I'm talking about. So I like to use food. We all love food. Great examples. So a homogeneous mixture, an example of a homogeneous mixture would be milk. Now, you're like, wait a minute, Miss Smith. Milk is not a mixture. Actually, it is. Milk has actually several different things in there. It's got fat suspended in the milk itself. So that is a mixture. But the milk, you can't really pull the fat out of there. It's got the same consistency throughout it. Now, another one that would be a good one would be Jell-O. I know I used Jell-O earlier. You can't pull, I'm not talking about Jell-O with the fruit in it. I'm just talking about straight Jell-O. You can't pull the sugar out of the Jell-O. So that's a good kind of litmus test for if it's homogeneous or heterogeneous. If you can pull it out, it's heterogeneous. If you can pull something out of the mixture, it's heterogeneous. If you cannot pull anything out of the mixture, it's homogeneous. Now, one that I would like to talk about, well, I'll give you the examples for heterogeneous real quick before I give you kind of a challenge question real quick. Okay. So an example of a heterogeneous mixture is salsa. You've got the tomatoes you could pull out, you have the onions you could pull out, you have the jalapenos or bell peppers or whatever it is that you can pull out. Another one, I like Lucky Charms. You can pull the marshmallows out. I know the other day they sell a bag just with the marshmallows, so go look for that one. Anyway, so here's the challenge question. Where does soda fall under there? Now, I'm not talking about soda with ice in it. I'm just talking about straight up soda with the bubbles in it. So go ahead and take a second and see if you take a guess, and let's see if you're right. Okay, so I want to point something out. I did say that soda has bubbles in it. If you have a mixture and you have 2 different phases, because bubbles are gas and soda's a liquid, then it's heterogeneous. Because technically, you don't physically pull the bubbles out, but you technically can shake up that 2 liter of Coke and all the bubbles are gone. That would technically classify as pulling it out. Okay, moving on. Let's talk about pure substances. So your two options for pure substances are elements and compounds. All right, so elements are single atoms or diatomic. Okay, y'all, pay attention to diatomic elements for just a minute. So I want to break down, let's talk about prefixes again, scientific terms. Di means two, atomic means atom, so that literally means two atoms. If you have a, I wouldn't call it a compound. If you have, and you're looking at something like O2, yes, there are two molecules there, two particles there, but because they're the same thing, O2, F2, I2, H2, He2, because they all have two molecules of the same thing, two oxygen, two fluorine, two iodine, two hydrogen, two helium, that means that it's a diatomic element. It falls under an element. So in a minute, I'm going to show you a picture, and it will look like this. I'll have one atom here bonded with another atom there. The atoms are the same color, they're the same size. That means that it is an element. So pay attention to that one. That's a common mistake. Okay, so let's talk about compounds. So we're going to say two or more elements chemically bonded. Okay, now you're like, wait a minute, Ms. Smith, they're chemically bonded. This down here, the diatomic element is chemically bonded. Okay, remember I said two or more. That's only one element. All right, one more thing before I move on to, I'm going to talk about the basics of the periodic table. Okay, so it's just real short and sweet. On the periodic table, you're going to see a whole bunch of boxes that look like this. So I want to talk about what are in these boxes and what do they mean. So I'm going to use carbon as my example. So you will see a giant C. That is known as the symbol. All right, then you're going to see carbon written down here at the bottom. That is the name. You will also see a number written out. It could be on the right side at the top. Sometimes it's on the left side at the top. Really doesn't matter, but it's the number at the top. That is the atomic number. And then underneath the name, you're going to have a number, 12.011. That is the atomic mass. Now, sometimes you'll find a periodic table that has a whole lot more things written in it, but you know, this is the basics. This is what you're going to come in contact with. All right, so I'm going to switch over and let's do some stuff with elements, mixtures, and compounds. Okay, so let's talk about elements again. So this is what I was talking about here, this bottom picture with the two yellow dots. That's what I was talking about before. That's a diatomic element. Okay, so it's a substance composed of a single kind of atom. They are not chemically bonded. A compound, more than one atom, two or more atoms that are chemically bonded together. Now a mixture, see, you notice that these are bonded together. They have those little black lines in between them. That's bonded together, so that's going to be a compound because it's got two more elements. This has two or more elements, but none of them are bonded. So that's technically a mixture of elements. Now, we're going to play a little game real quick. What I would like to do, I'm going to show you a picture, and I want you to guess, is it an element, is it a mixture, or is it a compound? Okay, so go with this one first. This is elements. Actually, to be 100% specific, this is a mixture of elements. Okay, next one. All of these pictures, all of these little atoms look exactly the same, so this is a compound. Okay, so the purple ones, those are elements. The blue and red ones are compounds. So this is technically a mixture of elements and compounds. All of these are the same, roughly the same size, the same color. This is just a straight up element. Okay, I have two different compounds here. That is a mixture of compounds. Now, this is a tricky one. Be careful with this one. These are the same color, the same size that are bonded together. This is an element. Specifically, this is a diatomic element. All right, so that's it for today, of the lecture today. Please go to Google Classroom and finish your